Let's look into connection of capacitors in mixed grouping, series parallel grouping. So let's consider something simple to begin with. We have some capacitors connected, say this way. This is 6 microfarad and this is 3 microfarad and this is 4 microfarad. This is 3 microfarad and this is say 5 microfarad. So our interest is to find the equivalent capacitance between A and B. In a circuit where there are a lot of capacitors, a lot of junctions, first identify the junction. There is a junction, more than 2 branches meet here, right? This is a junction, this is another junction, this is a junction. This is not a junction, this is a branch. So these are branches, right? This is a junction where branches meet. You start identifying a pair of adjacent junctions, between which you can find paths which don't lead to any further junctions. For example, if you identify this as a pair of adjacent junctions, this path leads to a junction. We don't want that. If you choose this pair of junctions, if you look this side, it leads to a junction, but we need to find paths which lead to, which have only branches, no other junctions. So these pair of junctions, adjacent junctions, will have, well, these are 2 branches. So we can simplify this. We can, this is a series branch, so this will be 2 microfarad. That's in parallel with 4 microfarad. That will be 6 microfarad. So we can replace all the 3 and have a 6 microfarad there. And that 6 and this 3 will be in series. So this is all gone to a 6 microfarad there. That 6 and 3 are in series, so 6 and 3 in series will give us 2 microfarad. So this all gone now. That's 2 microfarad and 2 and 5, 7 microfarad. That's the equivalent capacitance. So what you have done is you have identified a pair of adjacent junctions between which you can find paths which don't lead to any further junctions. So that part of the circuit gets simplified. Typically it happens away from the terminals, at a corner, at an end. That's one thing. Well, you found the equivalent capacitance that came to 7 microfarad, right? Another question that could be asked here is, say, suppose the potential between A and B, that is VAB, is say 18 volt. Say, what is the potential difference between C and B? What is VC minus VB? So we want VC minus VB. How do you work that out? Now, if you remember earlier, you replaced all the 3 by a 6 microfarad capacitor, right? This is what we had. So this is 5 microfarad capacitor and this is 3 microfarad capacitor, and all these 3 capacitors, got replaced by a 6 microfarad capacitor. So this is 3 microfarad. So this is B and this is A. This is 5 microfarad. This 5 microfarad is in an independent branch. If we look at these two, these are in series, and this potential difference between these two is 18 volt, we are told. So we could mark the potential, like we can assume one terminal is at 0, the other is at 18 volt. We are interested in potential difference, not really the potential. And this 18 volt is the potential difference across the branch of 3 and 6 together. So the potential difference divides in the inverse ratio of capacitances in series connection. So this is 3 and 6, so the inverse ratio 6 is to 3, that is 2 is to 1. Divide 18 in the ratio 2 is to 1. So 18 in the ratio 2 is to 1 is 2/3 part. 18 into 2 by 3, 12 volt. This potential difference is 12 volt. So if the potential difference is 12 volt, this will be 6 volt. And this, of course, 6 volt, that's what we can see here. This potential difference across 6 microfarad is 6 volt. Now, there is no 6 microfarad capacitor here. This has all been replaced. So you can go back. This is 6 volt. This is 0 volt we said, and this is 18 volt. So we can use now this 6 volt potential difference across this branch, 6 and 3, divides the ratio, inverse ratio, and 3 is to 6, 1 is to 2. So 6 in the ratio 1 is to 2. So that will be, well, you have 2 and 4. So you have 2 volt potential difference across this, which would mean 2 volt potential difference. 6 and 2 volt potential difference give us 4 volt. So this of course is 4 volt. So that's it. You have learned how to solve a circuit, which this fairly simple circuit, just not too many junctions, so it's fairly easy. This is a network of capacitors, and we're interested in finding, say, equivalent capacitance between A and B. There's a large network, there are multiple junctions. So what do? Well, these are junctions, right? These junctions, plenty of them here. So we find a pair of adjacent junctions between which you can find paths which don't lead to any further junctions. For example, if you pick this pair of junctions, well, this path leads to another junction. This path leads to another junction. So we don't want that. So anyway, suppose you pick this pair, you have paths leading to other junctions. But if you pick this pair of junctions, which are kind of to a corner, this one path between these two junctions, and this another path, another branch, and they are in parallel. So from a corner, generally they simplify. So this pair of junctions will, between this pair of junctions, we have one branch of 4C, another branch of 3C and 6C. Well, 3C and 6C will, they are in parallel, so that will give us 2C. 6C into 3C by 6, 3 plus 3C. So that will be 2C. 2C and this 4C, that will be 6C again. So this 6C and this 3C, that will be 2C. So this will repeat, 2C and then 4C in parallel, this will repeat. So you will get eventually 6, all this is gone, 6C, 6 and 3. So it repeats. So it will come to again 6C between C and D, and 6 and 3C, 6C and 3C in series will give us 2C. So effective capacitance between A and B is 2C. It's a large network, but that doesn't bother us because there is a repetition here. So let's do that again. Between these two junctions, which are to a side, we find paths which branches which don't lead to any further junction. So this and this. The 6 and 3, 2C, 2C and 4C in parallel. This will be all replaced by 6C. That 6C and this 3C are in series. That will give us 2C. 2C and then you will have a 4C here, right? So same thing, repeats. Eventually get 6C here. So number of capacitors do not matter as long as the branches are like this. So this is going to give us 2C, C effective. Another question that somebody can ask you here is if the potential difference between A and B is say 36 volt, if VAB is 36 volt, find the potential difference, say C and E, VC minus VE. What is VC minus VE? You could do this, well, like say replace all this up till here by 6C, this 6C, so you'll have something like this. This is A, this is B, we have C here, this is D. Replace all these capacitors by a single capacitor 6C. The junction C and D are in the original circuit and the equivalent circuit here, right? And this is 3C. This 6C is the equivalent capacitor for all these capacitors. So if you find the potential between C and D here, that you can take back that to the original circuit. So what's that? This 36 volts divides in the ratio of 2:1, inverse ratio. 2:1 will give us 24 volt and 12 volt. 36 divided in the ratio 2:1, 12 volt and 24 volt. So it's the 12 volt potential difference across this. So if you mark this as 0 volt and this is 36 volt, you don't need to do that, but we can do that. There's a 24 volt potential difference, so this will be 12 volt. This is 0. This is a conducting wire, so this is 0. So now this is 12 volt. So forget now this part, and this is 12 volt. And doing the same calculation as earlier, between C and D it is 12 volt. So all this is gone, 12 volt, and this can be replaced now, 6C. 12 volts divides in the ratio of 2:1. This will be 6C, mind you. So we have all this replaced. So let's draw that again if you want. So this is C, this is D, and we have this situation. This is E, this is F, and between C and D the potential difference is 12 volt, right? This is 0 volt and this is 12 volt. This is what 3C we have in the circuit, and this is the equivalent of all this. This is 6C. So 3C and 6C in series here. This 6C is the replacement for all these capacitors. So 12 divides in the ratio of 2:1 again. So that's 8 volt and 4 volt. 8 volt potential difference will give us 4 volt here. Of course this is 0 and this 4 volt. So what is VC minus VE? We got it, 8 volt. We got VE minus VF also, 4 volt. So the same ratio repeats. If you want to go further down somewhere, you can find that by the same logic. So this is what we get for that. This we got 12 volt, right? This is 36, this is 12, 1/3, again 1/3. So it repeats. 36, 12, 12, 1/3 is 4, 4, 1/3, goes on repeating like that. That's a large network, doesn't really bother us. We have here a large number of capacitors, all equal, C each, connected the way shown. Now I want to find the equivalent capacitance between A and B. Well, your usual trick, like what? Say, identify a pair of adjacent junctions between which you don't find, between which you can find paths which don't lead to any further junctions. So that happens in a corner. So this and this are nice parallel branches. This branch is C and C, that's C by 2, and that's C, 3C by 2, and then it gets messier. 3C by 2 and C are in series. We have to work that out, but it doesn't repeat like in the earlier problem. So what do? We use an interesting logic here. Now this is a slightly odd problem, and well, non-standard, but still that's interesting. So what do is this. Now if I remove one unit, say remove the first unit, so think of only these, you still will have a very large number of capacitors. So equivalent capacitance shouldn't be affected much by removing one unit. Like say, if you remove the last unit here, the equivalent capacitance between A and B will be nearly same as with that unit present. The reason being, if you apply a potential difference here, the charges that get stored as you go to the farther and farther branches would be smaller and smaller. This capacitor will have very little charge. So removal of that doesn't make a very serious difference. That's the logic. So you are saying that if you find the equivalent capacitance in these two, well, that is, you'll have, but if this is n, a very large number, between these two you'll have n minus 1, and n is large, so it doesn't make big difference to the capacitance. So you're saying something like this. Let the replacement for all these capacitors be CE. This is C. We do not know this CE. This is C. This is C. This is A and B. So your argument is that between A and B, the capacitance will be nearly same as C. So what is the equivalent capacitance in A and B? C and C are in parallel, that's C plus C, that is in series with C. So the equivalent capacitance comes to C into C plus C by C plus C plus C, so 2C plus C, and this is nearly equal to C. So nearly equal to, that we'll take it as equal. So you get a quadratic here which you can find to solve C. It's a non-standard problem, but fun to work with. So You don't always have a repetition like earlier. And, in this case, we have a nice logic to find the equivalent capacitance. So the whole idea is that if there were only, say, 4 such units, this CC approximation, this what we said earlier, like this, between A and B will be same as between these 2 points, will not work well. If there are 100 branches, say 100 such units, the approximation would be better. So this, you are told that n is very large, so your argument is pretty good, right?